Good morning to all. Today I am going to present my work which is on three-level inverters for induction motor driven electric vehicles. This work is carried out under the supervision of Professor Sanjeev Singh and Professor Shailendra Jain. I will start my discussion with introduction. Thereafter I will discuss about inverter topology, and thereafter I will discuss the switching sequence generation. Thereafter performance simulation we will discuss, and thereafter conclusion will be given, and at last references will be shown. So I am starting with the introduction. Due to climate change, advances in renewable energy, rapid urbanization, battery technology, and energy security, electric vehicles are becoming popular choice across the globe. Battery electric vehicles or pure electric vehicles are the most suitable choice to meet the objective of zero emission vehicles. To boost the commercialization of EVs in India, Indian government formed a policy in 2018 to mitigate the climate change and increase the use of ZEVs. European governments are planning to phase out the combustion engine vehicles by 2040. EVs with permanent magnets, synchronous and brushless DC motor have high initial cost because of PM, which requires neodymium, a rare earth element, and also due to its controller. More than 97% of rare earth element is mainly imported from China. Usually, a two-level voltage inverter is used for speed torque control of induction motor. It generates the required voltage in two-level output having high total harmonic distortion. Generally, the two-level output voltage is filtered with inductor capacitor filter. Nowadays, multi-level inverters are being preferred because of several advantages like reduction in switching stress, switching losses, filtering requirement, and electromagnetic interference. Three-level cascaded H-bridge inverter with level shifted sinusoidal pulse width modulation and offset scheme to reduce torque ripple at low speed operation is reported. Three-level neutral point clamped inverter with discontinuous pulse width modulation scheme to reduce the switching losses is also reported. Therefore, two basic MLI topology, namely three-level CHB inverter and three-level NPC inverter, are analyzed in this work for IM drive in EV applications. So now I will discuss the topology of inverter. This is the topology of two-level voltage source inverter. The switches of this inverter are operated with a switching sequence generated by PWM controller. This PWM controller operates with a control signal generated through a speed controller by sensing the speed error, which is a difference of reference speed and actual speed. This is the topology of three-level cascaded HV inverter. The switches of these inverter is also operated with the schemes which is discussed previously. This is the topology of three-level neutral point clamp inverter, and the switches of this topology is controlled with the scheme which is also discussed previously. Now we will discuss the switching sequence generation in detail. First, speed error is generated which is processed through a PI controller, and this output of PI controller is divided with the rated torque to get the unit amplitude, and this unit amplitude is multiplied with the three-phase sinusoidal waveform to generate the modulating signal. The three-phase modulating signal is fed to the PWM controller for two-level voltage source inverter. In this figure, the phase A of the modulating wave is shown, and this phase A is compared with the carrier wave of 10 kHz. The zoomed view is here for more clarity. When this modulating wave is greater than the carrier wave, it generates high signal, and when it is less than the carrier wave, it generates low signal. The switching sequence generator for S1 switch is just complemented with NOT gate to generate the switching sequence for S2 switch. In similar way, phase B of the modulating wave is compared with carrier to generate the switching sequence for S3 and S4, and phase C is compared with carrier wave to generate the switching sequence for S5 and S6. Now discussing the PWM controller for three-level inverters, and this scheme is used for three-level cascade HV inverter and three-level neutral point clamped inverter. So in this modulating wave is compared with two carrier wave. So this is the phase A of modulating wave, and in upper part it is compared with the upper carrier wave. When modulating wave is higher than the carrier wave, it generates high signal, and when it is lower than the carrier wave, it generates lower signal. And the switching sequence of S1A switch is just complemented with NOT gate to generate a switching sequence for S2S switch. And in second section, phase A modulating wave is compared with the lower carrier wave, and when carrier wave is lower than the modulating wave, it generates high signal, which is shown here, and when it is higher than the carrier wave, it generates the low signal. The switching sequence generated to S3 switch is just complemented with NOT gate to generate the switching sequence for S4 switch. So in a similar way, phase B of modulating wave is compared with the level shifted carrier wave to generate the switching sequence for leg B, and in similar way, switching sequence for leg C is generated by comparing the phase C of modulating wave with level shifted carrier wave. Now I will discuss the performance simulation results. Here the different torque is given 40%, 55%, 70%, 85%, 100%, and 120% in the case of overloading. And these are the results at 900 rpm, 1025 rpm, 1150 rpm, 1275 rpm, and 1430 rpm. So at rated torque and rated speed, the voltage TSD is 80%, while with 3-level inverter, the total harmonic distortion in voltage is around 40%. So there is a 50% reduction. While talking about the current TSD, it is around 1.7 for 2-level inverter, while it is around 1% in case of 3-level inverters. If we talk about the induction motor efficiency, it is around 82% in case of 2-level inverter, while it is around 88 and 89% for the 3-level inverters. If we talk about the power factor at rated torque and rated speed, it is around 0.68, while in case of 3-level inverter, it is around 0.82 and 0.82. If we talk about the voltage stress across the switch, it is around 5660 for 2-level inverter, while it is around 1500 in case of 3-level inverters. If we talk about the current stress through the switch, it is around 150 kilo ampere per second for 2-level inverter, while it is around 75 kilo ampere per second for the 3-level inverters. These are the voltage waveform for 2-level inverter, and this is a harmonic spectrum, and this is the voltage waveform and harmonic spectrum for the 3-level inverters. These are the current waveform and harmonic spectrum for 2-level inverter, and these are the harmonic spectrum for 3-level inverters. At steady state, there is a 1.5 Newton meter torque ripple in case of 2-level inverter, while there is a 1 Newton meter steady state torque ripple in case of 3-level inverters. These are the comparison carried out from the previous results. There is a 44 to 59% reduction in TSD with 3-level CHP, while it is around 43.92 to 59.29 with 3-level NPC. There is 50.57 to 45.33% TSD reduction in current, and there is a 75% reduction in voltage stress with these two inverters. There is around 49.40 to 52.16% reduction in 3-level NPC inverter, which is little bit higher than the 3-level CHP. There is a 2.75 to 42.86% improvement in efficiency of induction motor, which is little bit higher than the 3-level CHP inverter, and 18.84 to 44.68% power factor improvement with 3-level NPC inverter, which is little bit lower than the 3-level CHP inverter. Following conclusion has been carried out with this work. 3-level CHP and 3-level NPC inverter leads to reduction in TSDV and TSDI across the motor terminals, which will reduce the losses in the motor. Reduction in torque ripple of the motor, which will lead to silent and smooth operation of the vehicle. Reduction in voltage stress across switches and current stress to the switches, which will reduce the failure rate of the switch and cost of the switch. There is improvement in power factor and efficiency of ion with 3-level inverters. These are the references I have gone through for this work. Thank you.